So in our last video lecture we have found this curve, and this curve is about the strength of the compression member and the non-dimensional slenderness ratio, and I have described this lambda g. Okay, so this curve will give you the strength of compression member or column when everything is ideal. Okay, that means there should not be any imperfections, there should not be any eccentricity of load, and there should not be any residual stress. Okay, in case of a particular cross sections. So if every condition is ideal, then we can use this curve for to find the strength of the compression member. Okay, now in our actual practice we never get the actual ideal conditions. Okay, so there may be some imperfections, initial imperfections, then there may be some eccentricity of the application of load. That means you know what is eccentricity. And also, as we use some rolled steel section, so these sections are produced in the mills where these steel sections undergo some continuous cooling and heating, so there will be some residual stresses. Okay, so these conditions will affect the strength in our actual practice. Okay, so let us describe how these factors will affect, or how these factors will reduce the strength, okay, of a column member in actual practice. Okay, so what do you mean by imperfections? So that means the column will not be straight. Okay, so initially the column will have some minimum amount of deflected shape. Okay, so some minimum amount of deflection is present in that column. What will happen? So here this column should be straight, but it is having some deflection. Okay, initial deflections. Okay, now if we use this column as in our site, okay, what will happen? So as the load is passing through this line, the line on the left, okay, and the member line of the member is the right one, so this imperfection will create some eccentricity in the member. Okay, so in terms, it will at the very beginning it will be subjected to the bending moment. Okay, if initially it was straight, okay, the member will not be subjected to any bending moment. Okay, so what will happen? Suppose initially it is a straight member, okay, and we are applying or we are increasing the load. Okay, so this is a load deflection curve, so forget about this part. Okay, so we are increasing the load. What will happen? There will be no deflections. Okay, if it is initially straight. So when the load reaches this PCR value, or that is buckling load or crippling load, then the member will deflect. That means buckling will start. Okay, so whenever we are increasing the load from 0, where we are going up, and then after reaching this PCR it will show some deflection. Okay, and the deflection will go on increasing as it is a progressive method, as I have already discussed. Okay, now if there is some imperfections, that means this eccentricity or this gap, okay, then what will happen? So this is the initial imperfections which are present in our actual construction. Okay, then what will happen? So if we increase the load, so ignore this one, so consider the red one. Okay, so if we increase the load, what will happen? So there will be some deflection, because already there is some deflections. So from the very beginning the member is subject to bending moment. Okay, so this bending moment will progressively increase, as I have discussed. Okay, so if we increase the load, what will happen? The rate of increment of this deflection will be more. Okay, so it will go on like this. Okay, and when the load at any point is below this PCR, okay, the column will show some more deflections. Okay, suppose the load is this, okay, so at this value, okay, the column will show this amount of deflections, so it may not be serviceable at that condition, so we can say the column has failed. So the column is failing before reaching this crippling load, as we have derived this crippling load. So suppose you are assuming that at this crippling load the column should fail, but in actual practice the column is failing much lower than this load. Okay, so this is the effect of imperfections. So this is the cause, so I have drawn it like this. So this is a cause, okay, and this is the result. So result one. Now now these theories are proven by the test. Okay, so in laboratory some researchers have tested it. Okay, they have tested many columns, many compression members, and what they have found. So let us see this curve. So here I have drawn this curve, basically this part, from this part to this part, because this is the total story. Okay, so here this is the total story. Okay, now these star marks represents the data, or cross mark represents the data of collapse test. So the tested data are shown by this cross mark. Okay, now these cross mark are coming somewhere at these points. Okay, so if we take the lower value of this every test, sorry, so if we take the lower value of every test, then we can draw a curve. Okay, and it is easily noticeable that this curve is coming lower than this initial curve. That means the strength is lowered by these imperfections. Okay, so because when we are doing this test in the imperfect column, okay, so the points are coming here. Okay, so the some columns are points are coming lower below this actual curve, theoretical actual curve. Okay, that means what is theoretical, that is not correct for the practical applications. Okay, so they have tested different columns and different compression members, and they have just put it as a graphical format, and they have connected the lower point. Okay, so so they have got this lower curve, that is called lower bound curve. Okay, so now by this representation we can see how this initial imperfection affects or reduce the actual strength or theoretical strength of a compression member. Okay, now second one is eccentricity of application of load. So that is somewhat similar, because if there is imperfection, that means that the column is deflected. And second case is eccentricity, so that means load will not act at the CG of this cross section. That means from the very beginning the column section will be subjected to bending moment, so the effects will be somewhat same. Okay, so I will not describe it in for this second case. Now let us understand what is the residual stresses and how does it affect the behavior, okay, or the strength. Okay, now these sections are hot rolled and these are produced in factories. Okay, so in this production process the columns or the cross sections are subjected to alternative cooling and heating. Okay, so in these processes, uh, suppose let me draw a figure. Okay, suppose this is a standard I section. and this is produced in the factories. Okay, and if it is subjected to alternative cooling and heating, what will happen, this exterior part will cool down first. Okay, and this interior part, the fibers which is at the interior will take time, okay, to cool down. So in this process there will be some temperature stress, and some stresses will exist in these cross sections. Okay, so that what I'm saying, see, these exterior faces will be cooling down at the very beginning, but this interior part will not cool down at that rate. Okay, so there will be some temperature difference or stress difference actually. Okay, that's why some stress will exist here. So the stress will be maybe this here, uh, it is like this. So this is compression and this is compression. Okay, it will go somewhat up. So it will be, there will be some tensions. Okay, so similarly here also, and similarly here in this part it will be like this. Okay, so it will be subject to compression and like this. Okay, so in the bottom part also same thing. So these parts, okay, at this flange part, okay, this part is under the compression. Okay, some stresses are remaining whenever you are using these cross sections in our field. You are assuming that there is no stress, initial stress, but in practice there should be some initial stresses, that is residual stresses. Now what will happen, now, if we apply some compressive load here on these cross sections, okay, on this cross section we are applying some compression. So as this part, some part of this flange and some part of this wave is already under compression. Okay, suppose this stress is fr. Okay, residual stresses. Okay, so, but initially what we are, we have assumed there is no stress, so that means zero stress. But in actual practice it is this part, and this part will be having some initial compressive stress. So if we apply some load, okay, from, we are increasing the load from 0 to suppose PCR. Okay, uh, and maybe there is a P. Okay, so if we increase the load from the 0 point, what will happen, that means we are applying some pressure, that means it will be stressed. Okay, so maybe before reaching the yield stress, that means there may be some yield stress for this material. Okay, so before reaching this yield stress at some particular stress, that means fa. Okay, if this section is subjected to fa amount of stress, that means total stress is becoming fa plus fr. Suppose this fa plus fr is becoming fy, then this section will fail at these points. Okay, and this fa is less than this fy. Okay, but these at this cross, at this stress level, these parts are failing, but it was not supposed to fail. Okay, because it was supposed to fail at a stress of fy, but as these parts are already stressed by this fr amount, residual stress, so if we apply this fa, okay, that is extra, then with with this add sorry, with this residual stress, okay, this, that means fa plus fr, when this becomes is equal fy. Okay, when fa plus fr becomes fy, okay, these parts will fail. Okay, but this inner part will not fail. So again we are increasing the load in these directions, we are going the positive side, so we are increasing the load. So at some point we will be applying some stress fy. Okay, so that at this fy, every part should fail. Okay, or maybe as these part are under compression tension, so some compression will be required to balance that tension. Okay, so it may fail at higher stress and higher than this Fy. Okay, so let me brief this once again. So some part will be under compression in this any cross sections, and some part will be under tension. Okay, so when we apply some compression on these ready-made cross sections where some residual stresses are already present, okay, then we are increasing the stress. Okay, so zero stress and this suppose Fy and this F. Okay, so when we increase this stress, okay, then it is supposed to fail at this stress, but as these portions are already subjected to compressive stress of this Fr amount, okay, then when the applied stress, okay, makes the effective stress of Fy amount, that means we are applying the stress, suppose at a particular stress, that suppose this stress is Fa, and this Fa and this stress are making Fa plus Fr are making this stress yield stress. So when this Fa will make will create yield stress, effective yield stress, which will be subjected to these portions, so this portion will fail uh, before the failure of these portions. Okay, now, but it was not supposed to fail at this stress level, it was supposed to fail at this Fy level. Okay, now you can understand what is the effects of this residual stress. Now what I have already said in this part, so let us consider this part where there is a initial residual tension or tensile stress. So if I apply some compression on these total cross sections, okay, some compressive stress is required to balance this tension. And this this part may not fail at this stress level, at this stress level, so it may fail at this stress level. So you can it will look like that this part is showing more capacity, but actually this is not the picture, but because it is subject to initial residual tensions. Okay, so thus these residual stresses will affect the behavior. Okay, now this behavior is very prompt in this near about this Fy stress. Okay, that means this Fy stress is the governing stress in case of short column. Okay, because in case of short column, this part is short column, so in case of short column this is the governing stress Fy. But in case of long column, this is the behavior, that means in long column the stress is hardly uh, equal to this Fy. Okay, that means this residual stress will affect more, or it will this or the effect of the residual stress will have more effect on the short column, not on the long column, because this all everything is happening in this range near about this Fy range. Okay, so and this range is basically this short applicable for the short columns, not for the long columns, because for long columns the stress is Fcr, and which is much lower than this Fy. Okay, so as a whole we have to add these effects, and we have to prepare one chart or one graph for the strength. Okay, so let us do that. let us select the red pen. So in this axis lambda, in this axis fcd by fy, and suppose this is fy. Okay, here the curve will be just if you look at here, so curve will be just lower than this curve. Okay, so it will be a maybe a straight line behavior, and somewhat straight line, not exactly straight line, then it will be like this. Okay, so this curve will be will come lower than this elastic buckling curve. Okay, so if we add the all the effects, okay, so because in actual practice we never get the desired strength, like considering the ideal case. So now this buckling curve, so this is actually a buckling curve for column, from where we can find the strength. Okay, load carrying capacity or stress carrying capacity, that is fcd. Okay, now this buckling curve will be different for different class of sections. So as I have discussed, as I have not discussed actually, so I will discuss it later. So for different sections we have to categorize the sections based on the width by thickness ratio. Okay, so based on that ratio, there are four sections. So for four sections there are four category of cross sections. So we will have four different curve. Okay, because for every sections the behavior is different, because the governing factors are different. There are some effects of, on the behavior. Okay, so I hope uh, you will understand this, and from the next session I will move on to the numerical part. I will try to move on to the numerical part. Okay, thank you very much.